Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, hello everybody. So I'm giving this talk next Wednesday to Uppsala. So this is a work titled Fast Conservative Garbage Collection by me and Steve and Catherine. So garbage collection is ubiquitous. So GC implementations have two stark choices. They can either be exact or they can be conservative. So in those two, the current scenario is most of the high performance systems use exact GC. On the other hand, conservative GC is also very popular, but there is a problem. It's generally used only is less performance system. So systems that I will not say like don't care about performance, but systems that they use conservative GC more or less suffer from poor performance. So just have a look, what's the current state of the art performance of the conservative GC. So here we can actually see two state of the art conservative GC. One is the mostly copying collector and one is the Boehm, Dimmers and Weisers collector. The use case scenario, Apple's WebKit used the mostly copying. The Chakra VM for JavaScript, they use the BDW collector. And if we look at the performance, so this is normalized with state of the art high performance exact GC, which is reference counting Immix. This is our work in last year Uppsala. So mostly copying suffers from like 50% and BDW suffers like 16% performance. So in most of the cases, the 16% slowdown is a showstopper. So that's the current state of the art. So what's our goal? At least our goal is achieved same performance with respect to a high performance exact GC. So that's our goal in mind, and we start our work based on that. So why conservative GC? Because it has some advantages. First of all, you don't need any cooperation from the compiler or the runtime. If you need to implement exact GC, then you need to have stack maps. And engineering stack maps is a very challenging engineering work. And also conservative GC enables some compiler optimizations like code motion, which is not available if we use GC maps or stack maps. So it has got some interesting advantages, but what are the disadvantages? First thing, it needs to handle the ambiguous references. We will look at that just a slide after that. And as we showed before, it also suffers from performance. So our goal is design and implement a high performance conservative GC for managed languages. So now let's have a look what is ambiguous references. So there can be references from the stack to the part of the heap, and when we don't have any GC maps, the reference may be a pointers. So when we have a pointers, that means we must need to retain the reference and also all the things that are transitively reachable. So we don't know, because we don't have an exact GC map. So if there is a references from the stack or register to the heap, it might be a pointer. So we need to retain that and also all their transitive reachable objects. So what's the consequences? It's known as excess retention. If it's not actually a pointer, then we are actually retain those stuffs. So excess retention is the consequence of, if it's a pointer, then we have excess retention. It may be values. So maybe just some integers, but the problem is we also need to treat that as there might be a valid reference. So that means we can't modify them. So and we need to pin them. By pin means if we don't want to modify them, then we can copy them. So we can copy them just by pinning them. So the consequence is we have in the heap, we have maybe huge pinned spaces. Those are restricted that we can copy any of those. And next, for many GCs, we can actually have the metadata required for the GC in the object, not in the side. So if we have the metadata for GC in the object and we are not sure whether it is a valid reference or not, we can't actually change that metadata. So if we need to change the metadata, then we need to validate before updating any per object metadata. So how we can do that? We must need to have some form of filtering that guarantees that this is really a valid object. So those are the three consequences of having ambiguous references. So now we'll just have a look at what are the state of the prior work. So this is the non-moving conservative collector. So in non-moving conservative collector, we pin everything. So nothing gets moved. So the most widely used is the BDW. It is a free list allocator and uses a mark sweep collector. And the references must point to start of a valid, allocated, and live cell. So in this way, we can actually filter all the stuff that are not valid references. And this was originally implemented for a setting which is full conservative. So what's the problem with this? First of all, as we saw in our third slide, very poor performance for managed languages, and the settings that it is currently used now, the design that can move anything is actually a very conservative design. Next comes mostly copying. It's also known as Bartlett style collector and has got many variants. So it is basically a classic semi-space collector, but with two twists. One is the to and from space are not actually contiguous pages rather than a linked list of discontiguous pages. So when we have a page that is referenced by an ambiguous root, we just simply promote that page. We don't like those anything that in that page will not move. So that means in the non-moving collector we pin everything, but in mostly copying we actually pin page. So it might happen in a page there are like 20 objects, but there is only one root, there is only one reference to an object from the ambiguous root, but you can't actually move those 20 objects because only single object in that page is pinned. And for the validation, like the filtering, it actually introspect within the page to find out whether it is a valid reference or not. So what's the problem? First of all, semi-space actually suffers from huge collection cost. So among all the canonical GC, semi-space have the worst performance. And as we saw before, the mostly copying collector has also got poor performance for managed languages. So next we try to understand what's the reason behind that performance cost. So we did an analysis and we will have a look what we find out. So this is the number of roots that is returned when we have an exact GC and when we have a conservative GC. So this is like a first study of these things because in our VM now we have two different way of GCs. We have exact GC and we have conservative GC that we implement. So we can easily do this comparison what's actually happening. So this is average over 20 benchmarks that we run, and we find out the number of unique exact roots is on average is only 98. So the unique references from the stacks and register to heap. And all exact roots is actually 2.21 times of that. So we have like twice redundancy. And what about the conservative roots? We find out that there is only 4.7 times conservative roots, but among them only 1.6 times are unique. So that means when we have conservative roots is only 60% more than the unique exact roots. So it's not too much. Then we see one of the consequences of conservatism is excess retention. So we measured that by running. So we have simply two trays of the full heap, one with the exact roots and one with the conservative roots. And we find out And the difference between these is actually the excess retention. So the number of objects that are live by the conservative roots is just 44 kilobyte more than when we do an exact trace, which is only 0.02%. So this is very surprising, because the usual like idea about the conservative GC is that the excess retention is very high, and because of that we have poor performance. But we find out that for managed language, the excess retention is only 0.02% of the whole heap. So this is very surprising. Then we find the next consequences is pinned. So here at the first row, so we see that the actual pin bytes is only 14 kilobyte, which is 0.05% of the total heap. But when we have mostly copying, then we actually pin objects as well as other objects that reside in the same page. So with mostly copying, that number increased to 462 kilobyte, which is 2.1%. So which is also pretty low, because when we have mostly copying, the pin bytes is only 2.1% of the heap. But interestingly, among them 282 kilobyte are falsely pinned. By falsely pinned means the objects that are not actually need to be pinned, but they are pinned because they stand on the same page with the object that needs to be pinned. So the two things that's very interesting, one is the excess retention is very low, and also the number of objects that needs to be pinned if we use mostly copying is also 2.1%. So those two are thought to be the main reason behind the performance problem, but we find out that those two are very low. So what's the actual reason of the bad performance for? So now in our runtime we have, so in our VM we have the exact GC. So when we have the exact GC, we can actually have statistics for the exact roots, and then we have the same GC working conservatively. So we can actually go through the stack, read word by word, then we do some filtering, and then we can actually find the number of conservative roots at the same time, right? So if we do two scans of the stacks, one with the exact GC and one with our conservative GC, then we can have those statistics.
Do you get that? So I'm not actually sure what you're counting. Maybe that's why I'm confused. So the stacks and registers are what we're being conservative on, not the heap objects. Because the heap objects, you can use the type, either dynamic type information in JavaScript, or you can do it dynamically or statically in a language like C# or Java. So those pointers we know exactly. So if you either have a stack map that tells you exactly what the roots are, or you scan the stack and anything that looks approximately like a pointer, you treat it like a pointer. Oh, I see. So should I think of the 1.6? Does that mean 0.6 are misclassified? That's right. Okay. That's right. That's over the real ones from our exact implementation.
So, but if you say you know precisely the heap object,
yeah,
but it doesn't work, right? Because I take one of these, fake roots.
Yeah.
It points to something, and I don't know what it is. It may be a well-formed heap object, or just a wrong reference. Right?
That's right.
It's just somewhere.
So how do you solve that?
Yeah. So
Coming soon.
yeah,
Yeah.
yeah.
Okay.
So what we find out, actually the real reason behind this is not those two, excess retention or the number of pin objects, but the real reason behind the performance is heap organization. So here we will look those collected again, but now we will look at their exact counterparts. So now we have semi-space and mostly copying. So semi-space suffers like from 33%. So it's pretty bad, and mostly copying is also very poor. Semi-space have very good mutator locality because it's just a bump pointer, but the problem is because it has a very bad GC, so that's why the GC cost dominates its performance. Then the BDW, so we have mark sweep and BDW. So interestingly, BDW is only like 1% slower than mark sweep, but mark sweep still suffer 11% than a production GC. And the main reason behind this is it actually uses the free list allocator, and the free list suffers from bad mutator locality, and also free list suffers from fragmentation. So if we have a bump pointer and we have a free list, the allocator, so the 11%, like that performance is actually coming from just having a different allocator. So because we have a free list, that suffers a lot compared to a GC that have a bump pointer allocator. And if we look the RC Immix, it actually have good, it has a mark region based heap organization. We will look that a little bit later, which is based on Immix, and the performance is pretty good, which is like 3% better than the production. So again, we will reiterate our goal. So because we already have an exact GC with a pretty good allocator and performance, so that's why our goal is, can we have a conservative GC that performs same as the high performance exact GC we have. So the major point is, the problem is not the conservatism, but the main problem behind the performance is heap organization. So I mentioned about RC Immix. So instead of mostly copying, if we have RC Immix and pinned object based on RC Immix, then we can see this is the same stat from the previous slide, but when we have Immix or RC Immix, the number of pin bytes reduces from 2.1% to only 0.2%, because the pinning granularity changes from 4 kilobyte to only 256 byte, which is used by Immix. So if we use Immix, we can actually have reduced the number of pin bytes to 0.2% from 2.1%. So what are our findings? The direct cause of conservatism, which is excess retention or number of pin objects, is very low, and the main reason behind the performance is the non-moving free list heap structure. So this is not a good solution to use a free list allocator because it suffers from pure bad locality, and also you are having a very restrictive design that you are not moving anything. So those two are not a good choice, and we find out that Immix properties are very well matched to conservative GC needs. So so now we will just have a look how Immix works. So Immix is a marked region based collector. So here we can see Immix works on blocks and lines. So here we can see a block with 32 kilobytes block, and a block has several lines. So each line is only 256 byte. So object can span lines but can't span blocks. So if we just reconsider mostly copying, so in mostly copying we have 4 kilobyte pages. So in that case, object can span pages. So we have a 4 kilobyte allocation threshold. So the allocation done is just contiguously among the lines and blocks. So when we do the GC, is that got a simple mark phrase. So we mark an object as well as its line. So the objects, though the region that lines that are not marks are free, so those can be collected. And Immix also support recycled allocation and defragmentation. But by recycled allocation we means, so here is a block, suppose a block that has only 4 lines. So the allocator actually can allocate into those 2 lines. And in the same way, the allocator actually can move the 2 objects in the last line to the second line. So that means it can actually do the defragmentation, and the allocator then can reuse the last line also. So those two are very interesting property of Immix. Then we have RC Immix. So RC Immix actually combines reference counting and Immix. So what it does, instead of having a marked bit for each line, each line have a live object count with the reference count, and with this, instead of having object reclamation, we actually reclaim lines. So we just up the collection granularity from object to lines. So what we got, we have object local collection of reference counting, so very fast collection, but at the same time we got the great mutator locality that Immix offer. And also we exploit Immix opportunistic copy. So the Immix opportunistic copy is, so you can copy as long as the space permits. It's not like semi-space where you need to copy everything. So you can do the copy, suppose you have a copy reserve of like 1 megabyte, and you can copy as long as you can fill the 1 megabyte. If the 1 megabyte exhausts, then you can mark the object in place instead of copying them. So opportunistic copy is good because we will see when we have like conservative roots, then we can actually pin the objects and do an opportunistic copy of all other stuff. So by exploiting Immix opportunistic copy in reference counting, we can copy the new objects at their first GC, and we can also copy old objects by the backup GC, which is the cycle collector. So this is the first reference counting collector that do copy, and because doing copy we are eliminating fragmentation. So RC Immix collector combines reference counting and Immix and gives us very good performance. So what are the contributions we made? So we identify the real source of overhead is not conservatism but the heap structure. We design and implement a family of new conservative collectors, and we also design the fast conservative reference counter. And the final outcome is our conservative reference counting Immix collector matches the performance of an exact production generational collector, so which was our goal at the beginning. Now let's have a look how we achieve those. So our design. So the main two things we need to do, we need to have some form of filtering so that we can filter out all the bad references, and we need to have some form of pinning so that we can pin the references from the ambiguous root and move all other stuff. So to do the filtering, what we have an object map. So object maps used to filter ambiguous references. So this is simply a bitmap. So when we allocate an object, the bitmap records the start address of the object when we allocate. So at any point of time, we can ask the object map. So we have a reference, it is a valid or not. If the bitmap is set for that object, that means that's a valid object. If that's not true, then this is not a valid object. But we use the object map also to filter out dead objects, because in the stacks we might have objects that is already dead but it's still residing in the stack. So we also need to filter out those. So the only thing is the allocator sets the bit, but at the same time we also need to take care of when the object is dead. So the collector clears the bit for the dead objects. So this is, so for the,
So how can it be in the stack if it's dead? You said, oh, it can be dead, but then it's still in the stack.
yeah,
So to me, if it's in the stack, it's not dead.
no. So but that's, so when we, that's not a valid reference, right? So that's dead, but when we have an exact GC map, you will not get that object because that's dead. But when we have a conservative scan of the stack, that can still says,
So how do
okay,
you know it's dead?
yeah. So our object map knows it's dead.
How does your
Yeah.
object map know this?
Yeah. So
You know, it doesn't know it's dead, it just knows it can't be live.
yeah.
It can't be live.
It knows that. It knows that, because if it knows,
Reclaimed it on a
if it knows,
previous collection.
if it knows,
It reclaimed it on a previous collection.
So we'd have to
Oh, and
appear on the
later
stack
on,
later.
it, like this address magically appeared again.
well, no, it
Now
could
you-
just be buried in the stack somewhere, right? And that, or just, or a random integer that happens to point to something that once was
that's
live.
what I mean, right? Ah, right, I see how it happens.
Right.
It wasn't there a while ago.
Right.
Well, could have been
Now
too.
start, well,
No,
no, then
we
you
would
wouldn't.
have,
Right.
we wouldn't have
No,
elected it
if you're
then.
conservative, you wouldn't, right?
Yeah.
Right,
It has to like not be on
You're
any
right,
stack,
you're right.
and
This is
somehow
why I
some
was like-
local variable or something gets put back on there that shows there are hardly
But now
any of
you
these
still know.
pointers, but it does happen, right?
Okay, cool.
So it
Yep.
sounds like
Yeah.
global map.
Yeah.
And you know, if you have a conservative, concurrent collector, it would need to be updated concurrently.
Yeah. So
And do you have any measurement? It might be coming later on.
Yeah.
I'm just
Yeah,
asking
we have a
on
measurement.
the basically how contention is.
Yeah, so-
are there any
so if it's a concurrent collector, we actually need to update the map atomically, but it's also true if we have a parallel collector. So our conservative GC is not concurrent but parallel. So when we have parallel, we also need to take care of the atomic update. Yeah. So here, so the object map is actually a bitmap, as we say. Every time we get a ambiguous root, we ask the object map, is it a valid reference? Then object map says yes or no. So that's the function of the object map. How we implement that? When we allocate an object, we set the bit in the map to the start of the object. So simply, the object map granularity can be 1 bit for each 4 bytes. So we have an address, we allocate an object, we get the bit in the object map, set the bit, done. But the problem is we also need to, so when we do allocation, we have thread local allocation, right? So we can update those bit non-atomically for when we update the bit for the allocator. But for the collector, we need to clear the bit for the dead objects, but those cleared need to be done atomically because we have multiple collector thread running. For the GCs like reference counting, we can easily identify the dead objects because reference counting knows which object is dead. But the other GCs which does tracing, that's tricky, right? Because tracing only knows about the live objects. So what we did for the tracing collectors, at the beginning of the trace, we clear the whole object map, and when we do the trace, as the object are marked live, we set the bit in the object map. So in this way, we can actually keep track of the objects that are live after the last collection, the objects that are live in the last collection, at the same time, the objects that are allocated after the last collection. So those are the set of valid objects that we have.
So to follow up on Luca's question, that if you had a concurrent collector, even though you're allocating atomically, like you're the only one who's allowed to allocate into this block, but someone else could be collecting something else on that block. So then we would have to use
Atomic and on the allocator too.
right?
Or control where the collector is.
Right. Not let the collector get on the same page. You could do that,
Yeah.
which would be a lot faster, right?
The reason why I asked is in previous lives, I mean, Hotspot had this thing with the card tables and stuff,
Okay, yeah.
and it turned out to be a bottleneck in the long term. It's not easily solvable
In
general.
terms of
Of accessing from
the bitmap?
the card tables or the bitmap or something
Right.
from different threads while we're allocating and deallocating
Right.
and it could affect. That's why I asked.
Well,
Right,
there
right.
are bigger, I think there are bigger problems with the card table than that. Anyway.
Sure, but yeah.
That wasn't the biggest problem with it.
Yeah.
But in this case, we guarantee that when you're setting it for the first time, so the allocation path is just as fast as it can be.
Sure.
In this,
If you allocate locally on the thread and no
Right.
one else can touch it, then yeah, sure.
that's right, that's right. And so then the other stuff
Sure.
is happening at GC time when you can afford a little more overhead, right?
Okay, yeah. So this is not like anything new. So this is an object map that anyone can implement. So we have some interesting twists to that object map. First of all, so in the object map, but the bit sets are not done by the software instructions. By software instruction means I have an object, I get the base address and then offset, and I read the word and then set a bit with some masking. We don't do that. We use the x86 BTS and BTR instructions. So we have the base address and we just know which bit to set. We set that bit and we clear the bit. And the BTS instruction give us like 0.6% performance improvement. So we care about 0.6%. Why? We will show that a little bit later. And this is an object map. We say we can have a simple object map where we have 1 bit for 4 bytes. But our final object map is actually use 1 bit for 8 bytes. Why we can do that? The VM that we use, because of the object alignments and because some specific rule, we can easily identify the tip and the status word. So we, instead of using 1 bit for 1 word, we can actually use 1 bit for 2 words. So whenever we have a query to the object map, we can actually know whether it points to a valid double word, and then we can see, okay, if that's true, whether it points to a Sturgeon object. So 2 optimization to the object map. One is, instead of having the software instruction, we use BTS, and we actually have the resolution where we have 1 bit for 8 bytes, and that have a good result. We will see just a little bit later. So this is filtering, and then how we do the pinning. So instead of pinning in a page granularity like mostly copying, we pin on Immix line. So we have 256 bit lines. So when we have a references from the roots, we pin those objects, and all other objects can be moved. So that means with opportunistic copying, that means as long as the space permits, we can move a lot of stuff. And we can see only 0.2% of the heap is pinned with Immix, so we can actually move all the other objects. So this is the different filtering mechanism. So this here we can see, so this is all done on a mark sweep collector. So at the left we have the BDW. BDW don't use an object map. It just check whether the object start from a valid allocated start of a cell. And we have at the middle we have an object map, which is the default object map, and at the right we have our own object map, which is half resolution. So here we can see the object map gives, so if we look at the time, then the object's BDW is best, right? It only have 1% overhead, and the object map have 3.7, and the full object map is 6. I just said it wrong. The last one is the default object map. The middle one is our half resolution object map. So we have only, so the object map in mark sweep gives us 2.7% overheads. But the interesting thing is, when we have, but the BDW doesn't copy anything. So when we do copying, the advantage of copy actually outweighs the 2.7%. So with object map, when we do the copying, then the 2.7% is actually not much, because the result we will show. So let's just now look the methodology that we used. We used 20 benchmarks from Decapo, Spec JVM, and PJVB. We used JIX RVM and MMTK and latest machine and latest operating system. So first of all, the results. So at the our first contribution was we designed a family of conservative collectors. So we designed conservative reference counting, conservative Immix, our conservative RC Immix, as well as sticky Immix. So here all the exact collector and their conservative counterparts. So we can see, except the so all our conservative collectors, the difference between the exact and conservative is less than 3%. But so BDW is good with so BDW is only have 1% overhead than it exact, but BDW suffers huge than all the production collectors. But our conservative collectors, the difference is less than 3%, so which is pretty good, I think. So, and except reference counting conservative, every other collector actually copy. So we have low performance penalty for conservative collectors. Now that's our final result. So we show our reference counting Immix, which was like 3% better than chain Immix, which is the production collector, mostly copying, 45% and 12% overhead, and our conservative reference counting Immix is actually slightly faster than a production generational collector. So chain Immix is a production generational collector, which is a generational copying collector, and the reference counting Immix conservative is actually slightly faster. So we actually achieved our goal where we have a conservative GC for managed language with same performance as an exact tracing collector. So that improvement actually outweighs the little overhead that we have because of using the object map. Because object map definitely has got an overhead, because when we allocate, we need to set a bit. But because we can move most of the stuffs, that cost is actually outweighed by the copying. So what actually does, so this is, so all these for results are for Java. And this is another graph. This is based on different heap sizes. So this is actually space-time trade-off. So at the bottom we have from 1x to 6x heap size and the times. So this will like tells us the whole story of different GCs. So here we have the black, the blue is the chain Immix collector, and the green is the reference counting Immix collector that we have in the last year. So those are the two high performance exact GC. And what about the two state of the art conservative GC? So mostly copying, we can't even see that in that graph. So but BDW is good, but it's still in 2x it's like 12% slower than chain Immix. So we actually narrowed that gap. So our reference counting Immix, the light blue, light green one. So it's good, but it suffers in like very small heap sizes because of because we still have that pin space that actually suffers fragmentation. So and also we have that overhead of the object map. So all those results are actually for Java. So what does actually means for other languages? So we also tried to evaluate what our result, like how our result can help implementing like GCs for other languages. So first of all, one of the major thing is pinning, like how pinning affects stuff. So in Immix we see only 0.2% of pinning. So what we did an artificial experiment where we increase the pinning from to 8x. So if we have 8x pinning, like 1.6% of pinning, then the reference counting, conservative reference counting Immix have suffered only 3.4% of performance. So if you are implementing a language that have lots of stuff from the ambiguous text and register, and you need to pin a lot of stuff, if that number is 8 times than we have for Java, still the performance degradation is only 3.4%. So what we suggest in that case, so you need to do 3 things: quantify, modify, and implement. So by quantify means you need to quantify the ambiguous references in your target applications. Then you need to modify the heap organization so that it uses lines and blocks of Immix. And the reference counting Immix collector, the implementation is not so straightforward, but the implementing a full heap Immix is much easier than having a generational Immix or RC Immix collector. But if you just implement a full heap Immix, that will also give you 5% performance improvement. So if the ambiguous references in your application is in that ballpark of like 8x%, then it's a good idea to try to implement Immix, and we saw 5% improvement. So I believe you can also see that type of improvement in your application. So we also looked at the performance potential by changing the VM. So one thing that is very important, the code quality may dampen the performance. So in our VM, we intentionally crippled our runtime. We disabled the application code optimization, and at the same time we de-optimize the runtime code. So we try to have so our VM, it's a mature VM, but we also try to find the VM which is not so mature. That means it might have an interpreter. So in both of the cases, for both Immix and RC Immix conservative, we can still see some dampened advantages. So the one major thing is, as your VM is improving, you will see more improvement. So in summary, we have conservative GC, which is dominated by BDW and mostly copying, significant overheads, and we find out that not conservatism but heap organization is key to the performance. We have a new design. We use a low overhead object map, and line-based pinning, and our conservative reference counting Immix collector matches the fastest production. So which is a first time a conservative GC for managed language with the same performance of the exact generational collector. Thanks. Any question?
So I'm not too familiar with Baumdemmer's Weiser collector. How does it do the filtering without having the object maps?
Oh, yeah, so this is a free list allocator, right? So we have, so free list allocator means we have different free lists based on size, and so objects are allocated like, so objects are allocated based on like those size frames, right? Suppose we have free list, suppose a list with have all the objects maybe of size like 4 bytes or 8 bytes. So you have that alignment.
All the objects on a particular page?
There's several levels of tables.
Yeah.
The high level bit, it introspects the metadata
Meta.
that's already there for the free list. Once it gets to the block, it says
Yeah.
this is an allocated cell. It's perfectly aligned with the allocated cell.
Okay.
And it's,
Does that mean it has to traverse?
yeah.
It has a table that covers say 12 gigs, and then that table is going to have regions that cover say a megabyte, and then within that there's kind of a page. And that page has metadata. So it's a field. Like a meta site.
So everything on the same page.
Same.
So it has to
Same
use like
size.
the high bits, the one, and then it uses different bit masks for the address, but index 3 levels of tables. Yeah, but it basically just finds out which cell size it is, and it knows that that cell size is always aligned.
And then, yeah.
Is this an
Allocated cell
thing
and
on
live.
alignment? If it is, then it points to a valid,
Valid.
object. If it doesn't point to a valid object. Doesn't mean that it's actually the proper pointer, but it does point to a valid object.
So and then you can keep the metadata in a separate data structure, or you can keep it at the beginning of the block. But if you do that.
But they don't have any extra metadata. This is just the stuff they already have in the free list. This is the point. They're just leveraging the free list metadata.
Is that an optimization that you can also do in Immix, or have
No, so the
pages
problem-
with same size
So,
objects?
so as we see our cost of filtering, the free list introspection is very good, right? It gives only 1% overhead.
Right.
But the problem is with free list have some other disadvantages. So in free list you have like bad mutator locality, and also at the same time you fragment heap, right? Because of the size, so you can't copy objects. So no one copy objects in free list. So that means those two disadvantages, defragmentation and also because of the bad mutator locality, free list have good filtering, but because of those two, that filtering, so we can't use that filtering. So that's why in our collector we have the object map. And that's pretty good. So PDW, so our results suggest that the language that don't have, so languages like C or C++, PDW is actually a very good choice because you have just 1% overhead from the mark suite. And our last 2 slides actually shows that maybe you can also, based on your statistics, you can actually implement our Immix and other stuff for C and C++, and maybe you can get better results than PDW.
So one other question, you said early on in the talk that exact collectors disable some compiler optimizations like code motion.
Yeah.
What do you mean by that?
So-
Inhibits. Probably a better choice of words.
Yeah, inhibit. So you need to have GC maps, right? So
Yeah.
GC maps mean at some point of time you can trigger a GC, right? So there are some GC save points.
Yeah.
So based on that, you can move your code. You need, suppose you have like piece of code. This is a GC point or something. So you can't actually move your code.
Don't you just need to update the stack maps and introduce more GC points? New save points?
You can, sometimes you may need to constrain code.
It loses code
Because-
motion. There's no question about it, but it doesn't stop it, right?
Right.
Of course you have code
You
motion.
track proper type information, but say you do something that takes an internal address of an object in your GC map so
Things can't drift across the sequence.
but
You
things
have
like
to
some
take great
operations
care.
have to be atomic with respect to GC set points, basically.
Okay.
And so shifting part of that code across a safe point can then basically create a
But-
GC hole.
The GC set point has invariants associated with those invariants inhibit optimizations, period. Right, yeah.
So you
It's
can't
just-
like have some half address shoved up in a register, right? Some temporary calculation to get to the middle of an array or something, that can't cross the boundary of where you actually use,
some of it
point
can
to a
be-
valid object.
Some of it can be compensated with lots of engineering effort.
Right.
Like you could then have special maps which associate interior pointers back to registers that have base addresses,
It's not,
etc.
You
that's right.
could
It's not
engineer.
insurmountable, but it's a real pain in the rear, and this is why a lot of people punt and just go for the conservatism. It's like, it's too hard.
It might be clearer to basically say it's a lot harder to engineer a compiler that you type safe in terms of managing this stuff. Like, you can do some things, but
You can all, even with a conservative, you could kind of make a, make the address into half parts and leave it for a while and shift them
So there
together,
was
and by
actually
the
a
time
post
your
on,
object is gone, right?
there was a post on, I think, the BDW mailing list recently about a case where a compiler optimization caused a GC hole.
These kind of things.
Yeah, it was copying between two arrays, and it decided to keep the difference between the two arrays as like one pointer and the difference between them. And so then it was just using that as a stride. And so the second array actually got collected. So
It's such a cool bug, like it sometimes happens.
but it actually happened. People have been worried about this for decades or whatever.
That would happen
as a
with
whole.
conservative.
That's a conservative, like, that's the compiler that doesn't know about.
No, it wouldn't,
It
because
wouldn't happen with a proper conservative collector and a compiler that knows it's not allowed to do that kind of stuff. But in a fully conservative world where you just use C++ or C, then that can happen. It's scary.
So, amazing work. You should be more, like, blowing your own horn during the Oopsla, I think. Because it's really cool, I think. And you should, it could be the next Hans Bohm to make this really easy to use on the LLVM. Like to make a, Immix object thing that just link in and it'll work. Right? People would love that. Of course, I'm not sure if your supervisor would be happy if you spend a lot
well,
of time
he's
on that.
finished.
but
He can
finished.
do whatever he
Oh,
wants.
okay.
Free agent.
Do it, like make it not too, make it easy. Don't say people, oh, you just have to implement a little heap scan thing or something. No, just like
So-
link this.
So
it'll
there
do
are
it.
some people actually implementing our Immix, RC Immix stuff so they are trying to make it portable for C and C++. So,
Was that with the LV?
no, it's,
So just LLVM. Just
Just do it
don't
with-
care
do
about
it with the
rest.
compiler the whole
Oh,
world
yeah,
is
that's a
now
good choice.
using is great advice,
Yes.
right?
Yes. No, I mean, it is amazing, like, that you get so close, it's like a dream, like, I wish, often I wanted to implement, like, languages, and I want, like, more performance, and I just couldn't use C as my backend, basically, because of the garbage collection problem, and I'm not the only one, So, it would be great, like, I think many people would be super interested in having a reasonably high performance conservative collector, right? And this is I mean, I really, I believe you, but then I kind of don't believe you that I'll get to that level of performance, right? But hey,
But it's definitely faster than the, GC and object system you'd write yourself if you had to do it, right?
probably, right? No, I wonder, like, if I would do this for Haskell, would it really be like that good again? Like, and maybe, probably, right? Like,
For
but
Haskell?
they worked on Java like crazy.
You
Right.
said for Haskell.
Right. Yeah, I mean, it's an unbelievable number. Like it's, I believe you.
But yeah, I mean, I didn't expect we'd see this number at the end, but once we saw what was going on, it became immediately clear we could do this. Like, once we realized it was all about locality, we know that story very, very well.
Right.
We knew we could kill it. But we assumed it was going to be the things that
Yeah.
Refat showed, the pinning and the excess retention, and it wasn't.
Someone asked a question, it's not just the object you point to, but it's the object that they point to
Closure.
too. It's the
Right.
closure.
Yeah.
And so it's the case that the first level is small, but then the closure that keeps alive these extra objects is also small. But in theory, it could be the
It could
whole
be the
thing.
whole heap.
It could-
Right,
right,
in
yeah,
theory,
yeah.
it can be terrible,
Right, in theory,
right?
it does look right.
It's also an interesting question about how it is affected by heap size, because especially, I mean, maybe if you only care about 64-bit, that's not as big an issue. But one of the issues with conservative being at 32-bit VA, if your heap gets large, then lots of addresses
Look good when they're bad.
good addresses. But again, if you are already having base pointers, I think that helps you a hell of a lot.
It's it's deeply impressive because there's no low-hanging fruit anymore in garbage collection, right? So this is an amazing thing, right?
So,
yeah.
actually, the more, like, most of the amazing part was done before, like, the paper that we had.
But by you, right?
Hey, Chris, I just want to clarify a question you asked during the talk, and that is, so what Refat did, he built the system that goes really fast, but to do the analysis, he built another system which did had both implemented side by side and actually did 2 GCs at once. So you'd never use that in a production system, but that was a very, very useful analytical tool. So we did 2 closures for every GC. That was what Refat
And
did.
that's
was your
the
question,
trick
right?
to
Like, how do
doing
you
the
know?
analysis.
And-
Sorry,
and
that's
which
the
GC
better
actually
answer.
Won or whatever,
Well,
like
you
in terms
had-
of the actual collection. I'm just wondering whether the false retention
Oh, whether you kept
accumulated
killing it.
Yes.
or
Yeah, you
whether
did.
you actually
You
used the
did. We
real
were running a
GC.
conservative GC, but
So the
looking at
conservative
exactness.
GC. Okay, so the conservative
Exactness
GC
is
won.
on the
Dominated, yeah.
side.
So when you're measuring-
Exactness is on the side.
When you ran them
That's what
side
I
by
was
side,
thinking.
you're measuring all the properties that, other than locality, because that one,
Indeed.
yeah, because in that case,
You
you're blowing
can't
the
run,
property.
that, you can't
It
do
was non-performant,
performance.
right? It
Yeah,
was
yeah.
as slow as a dog, but
Yeah.
because it did 2 GCs every time.
But that's how you eliminated the other two.
Right.
sources.
That was just an analysis tool,
Gotcha.
which was as complicated as the algorithms are, right?
So this actually, you should show, like if you give your flop up, have a slide where you say, look, I ran 2 collectors and now I know exactly
Right.
Yeah.
the exactness property. Now you showed like 2.2, 1.6, and he was kind of asking it, and even like, am I dumb? Can I ask this, right? So you should really just make that.
He was not thinking that.
You were like a little like, I hope it's the right question. But I mean, it was a huge thing that you can do this kind of analysis and that you can talk about this. It's really
So-
cool, right?
so-
So make it more clear. I think
That's
that you
like,
did this.
that's the like main point. So in my PhD, so Steve Catherine and so Daniel also was my supervisor. So Steve and Catherine, they're very interested in those analysis stuff. So in most of the time,
Really
It's really interesting that you have a kind of a story behind this. It's
Yeah,
not
yeah,
just-
so that's-
just that you built a collector,
Yeah.
it's that you just discovered properties of what was
Yeah,
going
that's
on.
like-
Interesting.
that's exactly right.
So the hardest thing about GC, what I
It's a
found that
story.
It is a story.
it's very easy to get good performance, but it's hard to describe how you are getting the good performance. So that's the thing, you must need to have some kind of analysis. So.
It's not really easy. to
Yeah.
get
No,
good
it's
results. It's also challenging to do that. But
Well,
then
I guess if you put the parameters in right, you usually get a good number out. It just doesn't mean anything.
you just don't know what it means. Right, it is true that it's very hard to know what your number means.
Well, Refat's he had 3 papers in his PhD, and the first one took the overhead of reference counting from 35% to 10%, and the next one took it from 10% to 0, and the next one did this. So yeah, he's had a charmed experience with killing performance
Probably it's
bugs.
like the performance part was easier.
All right, thank you, everyone.